Hello everyone. In this video, we will learn how to design and prepare a buffer in a laboratory. This is one of the most important skills that you will learn in a chemistry class. First, why do we need to prepare a buffer? When we do experiments in the labs, we often run into a situation where you need to maintain the pH of a reaction mixture because the reaction that you are interested in is efficient at a particular pH. So we prepare a buffer solution and conduct the reaction in that buffer. Or let us say you are characterizing an enzyme or an RNA molecule or any other biomolecule. The structure and properties of these biomolecules are strictly dependent on the pH of the solution. Therefore, these biomolecules are always suspended in a buffer solution that maintains the pH. Earlier in the course, we learned that a buffer has a weak acid and a weak base that are conjugate to each other. 2. An ideal buffer should have approximately equal and appreciable amounts of acid component and the base component. 3. The pH of the buffer can be calculated by Henderson and Hasselbalch equation.
It is very important to realize that we can change the ratio of the concentration of the base component to the acid component in a buffer solution to change the pH of the buffer solution.
We are going to use these 3 points to design and prepare a buffer solution in the lab.
Let us say we need a pH 3.7 buffer to study activity of a particular enzyme. A buffer has a weak acid and weak base that are conjugate to each other. So the first thing we do is choose the conjugate acid-base pair in such a way that the pKa of the weak acid component is as close to the desired pH as possible. We need a buffer whose pH is 3.7.
Therefore, we need a conjugate acid-base pair whose pKa value is as close to 3.7 as possible. We go into the lab and check the inventory for all the available weak acids. Let us say we found out that there are 3 weak acids available: formic acid with pKa 3.7, nitrous acid with pKa 3.4, and acetic acid with 4.7 pKa. So which weak acid would you choose to make the buffer with pH 3.7? Luckily, the formic acid's pKa value is 3.7, which is identical to the desired pH. So we pick formic acid to make our buffer. In the next few slides, we will learn why the pKa of the weak acid component of the buffer solution should be as close to the desired pH of the buffer as possible. In this slide, we will learn why the formic acid-formate ion is the best conjugate acid-base pair to prepare a pH 3.7 buffer. According to the Henderson and Hasselbalch equation, we know that there is a correlation between the pH of the buffer and the ratio of formate ion concentration to the formic acid concentration. If we plug in the pKa value of the formic acid and the desired pH value of the buffer in the Henderson and Hasselbalch equation, we can find out the ratio of formate ion to the formic acid present in the buffer. Solving for it, we get the concentration of formic acid is equal to the concentration of formate ion. We know that the acid component of the buffer, that is formic acid, neutralizes the added strong base, and the base component of the buffer, that is formate ion, neutralizes the added strong acid. Now what it means is that the buffer with equal concentrations of acid and base component can buffer equally well against external acid and a base, which is an ideal buffer. Why can't we use a weak acid whose pKa is not close to the desired pH of the buffer? In the next two slides, we will try to answer this question. In this slide, we will learn what happens if we choose the acetic acid acetate ion combination to prepare the buffer. The desired pH of the buffer is 3.7 and the pKa of the acetic acid is 4.7. As we can see, the pKa value of acetic acid is not that close to the desired pH. If we plug in the pKa value of the acetic acid and desired pH value of the buffer in the Henderson and Hasselbalch equation, we can find out the ratio of acetate ion to the acetic acid in the buffer. Solving the equation, we get the concentration of acetate ion divided by the concentration of acetic acid is equal to 0.1. That is, the concentration of acetate ion is 10 times smaller than that of the concentration of acetic acid. Since the concentration of acetate ion, the weak base component of the buffer, is really small, it cannot effectively buffer against an external strong acid. Therefore, this is not an ideal buffer. This buffer, however, has a large acid component. Therefore, this would be a great buffer if you wish to use it against the external strong base. Most often, we make buffers that can buffer equally well against external strong acid and external strong base. That is, a buffer in which concentration of the base component is approximately the same as the concentration of acid component. In the next slide, we will check if we can use the remaining weak acid to make a pH 3.7 buffer. In this slide, we will learn what happens if we choose the nitrous acid nitrite ion combination to prepare the buffer. The desired pH of the buffer is 3.7 and the pKa of the nitrous acid is 3.4. As we can see, the pKa of the nitrous acid and the desired pH of the buffer are not identical. However, they are very close to each other. If we plug in the pKa value of the nitrous acid and the desired pH value of the buffer in the Henderson and Hasselbalch equation, we can find out the ratio of nitrite ion to the nitrous acid inside the buffer solution. Solving the equation, we get nitrite ion concentration divided by nitrous acid concentration is equal to 2. In this buffer, the concentration of the nitrite ion is 2 times as much as nitrous acid. Therefore, it will be more effective against an external acid than against an external base. The order in which I would use these three weak acids to prepare the buffer is formic acid formate ion, followed by nitrous acid nitrate ion, followed by acetic acid acetate ion combination. You opened the formic acid container and realized that you do not have enough formic acid to make the buffer solution required. So we go to the next best option, that is nitrous acid. The majority of the times in a lab, you will end up preparing a buffer whose pKa value is close to the desired pH. Very rarely we can find a conjugate acid-base pair whose pKa value is identical to the desired pH. In the part 2 of this video, we will learn how to prepare this buffer in a lab.